Okay, so what I'm going to talk to you about is about a few things for us library writers, how to organize our work and what to do when we encounter certain kinds of issues, and how to try to accommodate the needs of the application programmer. So what we have done in the context of EoCoE is to do some work in work package 1, which is called a transversal basis, meaning that there is a bunch of us who are doing work on various algorithmic issues. And we started talking with the application people to see what their applications would look like and what the problems look like and what the requirements were. And typically the basic answer that we got, we want to run a simulation, we want eventually to run a simulation of 250 million degrees of freedom for a linear system that is this big with this condition number, and we want to solve it as fast as possible, etc., etc. So we, obviously, we started by talking with these guys and see, well, can you, let's identify what your program looks like when it is translated into this sort of technique. Because what we do is to take a system, AX equals B, which is large and sparse. Now, AX equals B sounds like it's a very simple problem. And, well, actually, I would contend that there are very few things that we human beings are capable of actually computing, and linear systems are one of them. The other being integrals and perhaps Fourier transforms and not much more, exactly, or roughly. And these are the really the workhorses or the building blocks of most scientific applications. And in fact, I think this problem here, when A is large and sparse, accounts for something like 40 to 50% of the machine cycles burned in every supercomputing centers. Another 20%, 20-30% might be eigenvalues and still within linear algebra. Then there are FFTs, and then there is everything else. Those are, I mean, very rough numbers, but it's the order of magnitude is correct. So I must also say that I feel a little embarrassed by not having nice simulations of the northern lights or stuff like that to show you. But as Dan Knuth is fond of saying, our role is to be at the bottom of things. We are to provide you the basic blocks, and so don't expect anything fancy from us. I would expect you to produce something fancy with the building blocks we give you, hopefully. So let's review what the needs from our application folks are. First of all, we are dealing with parallel programming. Well, parallel programming is about three things: data location, and data location. As we have learned today, moving data is extremely expensive. Well, we know we have been told this for quite some time now, and we are finally getting it. You should never move data unless absolutely necessary, which means that where you place data is essential to gain performance. Therefore, you want to be flexible in data distribution, which also means that we as library writers should not mandate a specific data distribution, or at least we should put very, very minimal constraints. The data exchange operations, when they are needed, well, they should be implemented efficiently. They are cumbersome, they are boring, and they can be done the wrong way. Well, I have a question at the very end, but that will have to wait. There is a very important thing, is that the lifetime of the applications of you folks tend to exceed the lifetime of the machines you're running your applications on. And since the matching between a code and a machine, at least as far as I am concerned with sparse matrices is largely a story of data structures. That means that I need to be able to move from one data structure to the next without changing the overall, let's say, algorithmic layout or the, let's call it the workflow of your application. Much like what Luigi has presented before, you have the overall algorithmic. Are we getting back to flowcharts, maybe? Kind of. Yeah, actually.
Hopefully DSLs.
Hopefully DSLs, yes. That's in some sense what I'm trying to do. And of course, you want to have a separation of concerns between the application and the linear solver, because solving that problem is very, very hard. The fact that it is very hard is proven by the fact that people like me, like Bo Kagström in the audience, and other people have built entire scientific careers on doing this, and there is still no end in sight. We are nowhere near the end. But I would also want to point out that we have been hearing about weak scalability and strong scalability for quite some time. But actually, what I hope to convince you is that there is also a very important thing from our point of view, and that is algorithmic versus implementation scalability. What do I mean by this? Well, implementation scalability is the nitty-gritty details of how fast your code is running, depending on the size, so whether you're doing weak scalability or strong scalability fits here. Algorithmic scalability, what happens to the overall history of your algorithm as you move from a serial prototype to a moderate-sized cluster to a very large machine? Can you ensure a consistent behavior of your algorithm? Is your serial algorithm the best, the most efficient serial algorithm capable of keeping that efficiency, that advantage when you move to a parallel machine? That is a big question, and it's part of the research that we have been doing in the last few years with my colleagues. And of course, we all heard that our computers are going to become stranger and stranger with every passing supercomputing edition, and so we are now well into the mayhem of dealing with heterogeneous platforms. How do you do that? Okay, so let's go back to this thing that I started. Now it's a long time ago. It even influenced the work I did when I was in IBM in a previous life, and I was working on the ESSL on their scientific library. So it's a library that is designed to provide you with Creedle solvers for general or symmetric positive definite matrices. And one of the ideas was to abstract away and to provide a flexible way to dealing with the internal formats in which you store the matrix. So you have heard, probably if you deal with sparse matrices, you've heard of storage by rows, storage by columns, coordinate storage format, LPAC, you name it. And I have a slide later in the presentation where I hope I will surprise you about one more thing. But the point is that all of these are now pushed down at our level where they belong. The application programmer should not deal directly with them. That's a very, very, very bad idea. Of course, we cannot do away with message passing these days. It means MPI. Tomorrow, is there going to be a life beyond MPI? At some point, we'll see. Probably MPI has exceeded, I suppose, the wildest expectations of the people who designed it originally in terms of a lifetime. But it's beginning to see that there are some limitations to it, especially, and in my other life, I'm doing some research on PGAS languages. The funny thing is that with PSBLAS languages, you can get better MPI than MPI. Why? Even if you're using MPI as your transport layer. That's because using the advanced one-sided communication of MPI is hard from the application point of view. So most people don't do it, unless it's a really mission-critical project. It's hard to get things right. Anyway, so this is the latest paper on this is from 2012, and then we developed a plugin of preconditioners. Now we might describe what a preconditioner is. A preconditioner is an approximation to your linear system to some extent. So you want a method that will approximate your matrix. It will approximate it fast. It is fast to compute it. It is fast to execute it. And it should approximate your matrix well. You want all three characteristics, but you only get to pick two. You cannot satisfy all three of them at the same time, because otherwise, if you want it to be a perfect approximation of your original system, it is as hard to solve as it is the original problem. So you don't get anything on the other two. And you can run all permutations of this. So what we did was to try and implement what today are considered the best preconditioners at least for problems coming from the discretization of PDEs, the algebraic multigrid variations, and there are zillions of variations of these kind of things. Algebraic multigrid is good because it provides algorithmic scalability. The promise that it gives you is to have a number of iterations that is constant or nearly constant as you move from your best serial execution to your parallel execution, which is not the case with the classic preconditioners that you can find. So what is the idea behind multi-level preconditioners is that you start with your discretization mesh, and then you notice that the error on the discretization mesh has a distribution in frequency, and you really want to capture and try to reduce the components that are at very low frequency, but those components that are at low frequency on the base mesh become high frequency if you subsample the mesh, and you can apply this thing recursively. What if you don't have a geometry? Then what you want to do is to use a topological multigrid. So you look at the topology of your matrix, of your mesh, and which is, the matrix is a representation of the topology of the mesh, and then you want to look at the strength of connections among the various nodes, and you define the coarse mesh through this method. And this is a problem, a big problem, because most algorithms for detecting and aggregating nodes are applied in a decoupled way, because applying them in parallel would be just too cumbersome. But when they are applied in parallel in a decoupled fashion, every core for itself, then they begin to lose load balancing. So that's not nice, not at all. Okay, so let's see. Okay, so what does an application look like? Well, you have this thing called the various objects. You initialize your preconditioner, you set its attributes, you build it, and you apply inside the Krylov subspace method. That's about it. So we keep a very simple strategy. Applications we had in the past, we have grown from a few 100,000 cells in reactive flows to tens of millions of cells in large eddy simulation, and then again tens of millions of cells. With this application, which is a very nice one, we are doing image processing, or more specifically contour detection by linear algebra. So that's very satisfying for me as a linear algebra person, and we are doing it on a heterogeneous NVIDIA Intel platform. Okay. Now, the heterogeneity. This thing here, from a software design point of view, is the key thing. This is a variable that you define in your main program and you pass to the library code. That variable contains a new data structure that the library never knew about. You never recompile. You define a new variable, a new storage format. You pass it through this, and it works first. So you are protected against changes over time. Second, this variable is local to each process. Who is to say that it has to be the same on all processes? If one of the threads is acting as a front end for the GPU, you can pass a GPU-specific variable. If it's running on a normal CPU, you pass a CPU-specific variable, and the thing will keep working. Of course, getting the load balancing right between GPU and CPU is another kind of worms, but you get the idea. At least we are taking out one of the difficulties for you by concentrating on a design that allows you to put in place some plugins. You develop the plugin in a completely orthogonal, or in a completely separated way from the base library, and then you link it via the main program. So what did we do during the first year of EoCoE? Well, we did a few optimizations for the GPU plugin. We did some additional profiling and tuning. We added 2 new Krylov solvers, flexible conjugate gradient and the GCR, and we added the K-cycle, which is a preconditioner proposed by Ivan Notai, that does preconditioning by a couple of steps of an auxiliary of a secondary Krylov method. But the most important thing that we did was to use graph matching techniques for defining the aggregation. Why use graph matching? That's a very interesting story, because it's the big advantage is that you can control very cleanly and very strongly the degree of coarsening that you get in such a way that it does not lead to load imbalance. So the basic strategy is based on strength of aggregation, the strategies that were introduced in the late 90s by Vanek and Brezina from University of Colorado. They tend to produce very skewed loads on the matrices coming from the EoCoE application, whereas this one has worked wonderfully. There is a catch here, and the catch is that computing the matching is a very expensive operation, especially if you want to have the exact optimum matching, which is what you have from this MC64. That's the standard library from Harwell, from the group by Ian Duff. And so we tried to do 2 different approximate algorithms. The first one was originally published by Praise, and it is guaranteed to give you at least 50% of the optimum in a much lower time. And then there is an interesting one which is based on an auction algorithm. You wouldn't think of using an auction algorithm inside a scientific computation, but and this is again from the next edition of the Sparse direct methods from the group of Ian Duff. It's used, matching has a long history of being used to do pivoting in sparse direct methods to bring heavy elements on the diagonal. So let's see. The first example is from Alia, from a CFD code used to simulate a wind farm design, and we have a few dimensions from 800,000 elements to 2.5 million elements. This is, let's say, this is the test run to figure out whether we can do something. So we are using flexible CG with algebraic multigrid and block Jacobi and EoCoE on the solvers, and this is the kind of timings that we get. And I think this one is done on, I should have also another. So this one is important because I'm going to show you later on a comparison with the GPU code. But, and as you can see, this is the effect of algorithmic scalability that I was talking about. When you go from one processor to multiple processors, you get a jump in the number of iterations to convergence. But after that, we are able to keep the things under control. So, yes, we are losing something by going parallel, but it's not a desperate situation. Another example we got from Wendy Sharples at Jülich. It's a groundwater modeling, and we have a few examples with different degrees of anisotropy in the modeling of the diffusion, and all test cases are of about 1 million equations. And yeah, that's what the matrix looks like. And this is the sort of behavior that we got here on, I think these runs were done on Mare Nostrum. And as you can see, if you use a simple normal one-level preconditioner, you get order of a few hundred iterations, plus you get a change as you grow with the number of processes. Of course, these 15 iterations are, each one of them is heavier than a single iteration of this one, but you still get some improvement in the runtime. So this is something that is interesting, and again, we are able to keep the scalability, the algorithmic scalability under control. And this is another different example with different degrees of anisotropy in the problem. The other thing is that there is a slight difference in the number of iterations if you switch from one matching algorithm to the others. As I mentioned, these two algorithms are not exact matchings, but they are good enough, and they give you a much better time for computing, for setting up the preconditioner, which is, of course, a problem. Okay, so let's skip this one for the sake of time, and let's move to GPUs, which is what everybody seems to be using these days. And here I'm not showing the theoretical peak gigaflops, but the theoretical peak bandwidth, because for sparse matrix computations, this is what is important. It doesn't matter how many gigaflops you can extract from dense matrix multiplication if you're doing sparse matrix vector product. This is what is limiting you, and in fact you can see that there have been some instances in which the bandwidth has remained flat across models, meaning that you were supposed to get better performance from a new card, but you didn't, because it really wasn't improving in the way you wanted. Okay, so what data structure should you use on a NVIDIA GPU? I have this paper that came out in January, February on ACM TOMS, and these are all the storage formats that have been proposed only for NVIDIA GPUs, and just in the last 4 or 5 years. Okay? So do you really want to deal with all of them directly? No way. So what we did was to implement these software engineering techniques based on the concept of state and prototype design patterns, and it's detailed in these 2 papers here, the kind of technique that we implemented to hide this complexity. Unfortunately, we also have to add another aspect to this, that is, most normal preconditioners do an approximate factorization of the matrix, but then if you have an approximate factorization, most often you want to solve a sparse linear system. And this is a big no, no, no on GPUs. there is no way to implement efficiently the solution of a sparse linear system on a GPU. Or, to be more precise, the efficiency depends on how many non-zeros you have. So if you have plenty of non-zeros, then you might be able to get efficiency. But if you're doing sparse, you don't want plenty of non-zeros. So you can't do that. So what you want to do is to have an approximation to the inverse that's done by the product of sparse matrices, so that you can use the matrix vector product itself to do the preconditioning. And this is something that we explored with my colleague, and we had the paper late in 2016. So does it work? Yes. Look there. The time for solution on the CPU is 5 seconds. Time to solution on a GPU is 0.92 seconds, even if the number of iterations is larger. Now, as you can see, the number of iterations stays constant. This is algorithmic scalability. This is algorithmic scalability. But at 6 GPUs, this is saturating because the GPUs are so much faster than a CPU that with the current size of the test problem, the communication time was beginning to become dominant, which is something that on a normal CPU you only begin to see at a very much higher. So are we ready to tackle larger problems? Yes, we need larger problems to scale beyond what we are seeing here, but we are capable of doing that. And as I said, the solver and the preconditioner code are not even recompiled to run on the GPU. All the magic happens inside the data structures that keep a copy of their data on the GPU side of things, and that sort of stuff. Okay, so I think I'm within time, and I'm sure that Bo will agree with me that there is no sign that we are going to be out of work anytime soon, given the challenges we have. We have new specialized architecture to look at. Everybody these days is wondering what, if any, the long-term effect of nice landing will be on our algorithms. We have algorithmic scalability issues, how we deliver consistent behavior for iterative solvers in the face of parallelism, heterogeneity, and power management. That's a big question mark. What will the programming model of tomorrow be? Will we ever be able to go beyond what MPI looks like today? I have some ideas, but this is perhaps not the best forum for it. And the other important thing is what to do with multi-scale and multi-physics problems, couple models, tools that work on submodels and then communicate through scripting languages, adapters or conduits, however you want to call them. Well, it's going to be an interesting life. And of course, it's tough to make predictions, especially about the future. Last but not least, we are running an EoCoE mini symposium in the LSSC 17 in Sozopol in June. And I hope to see some of you there. And that's about it. Thank you. And I think